vector function. So here's a vector function. Notation is, it looks like just a regular R. In the book, it's going to be block. It'll be bold R. But by hand, I draw it with an arrow because it's a vector. Notice the vector. And in this case, each coordinate is a function. Each coordinate is a scalar function, which is just emphasizing that it's not a vector. So this curve has cosine t for x and sine t for z, which means along the y-axis, which is this axis here, along the y-axis, this curve goes around. It goes around that axis. So when you have this sort of thing, look at what you have. We're in 3D, 1, 2, 3 coordinates, but the curve is itself one-dimensional, but it needs 3 dimensions to exist. It's one-dimensional because it's just a string of points. It's got, if you were a bug, you could go forward and back on this thing, and that's all. You could, if you went to the left, you'd leave it. If you jumped up, you'd leave it. So it's one-dimensional. It's not a surface. It doesn't have area. All it's got is length, but it's twisty. It exists in 3D. Now the book talks about a thing called a projection. Now if you looked at this curve straight on to the y-axis, trying to get it straight onto the y-axis, it makes a shadow, not quite a sine or cosine curve, but it is a curve that's going up and down when you look at it that way. Now if you look at it straight down the y-axis, you get a circle. And that's the cosine t, sine t part. So these are called projections. Here's the projection into the xz plane. Here's the projection into the yz plane. And it's also when I pull back and you look at the full thing, you look at the full curve. It's not a projection anymore. You're looking at the whole thing. Here's looking at the whole thing. We see this thing, and this is called a helix. This kind of spiral. It's the spiral that you have for your spiral-bound notebook. It's the spiral that you get for DNA. Come on, I'll be able to let go of you. So we're going to study some properties of this thing. So let's make the line tangent to the curve. Well, to be tangent to the curve would be something like this. You'd have a line tangent, so it's pointing tangent to the curve. It's got its tail on the curve. Let me see if I can get that so my hand's not blocking it so much. Yeah, so here's a tangent. So you can see the tangent riding this curve. It's doing this. It's coming around here. So it's also like if you were ever on a spiral staircase and you held a pencil along the spiral staircase as you walked. With the tail of the vector being on the spiral staircase, making a tangent. So it's a really well-behaved tangent. It doesn't jump around like crazy. Anyway, so r prime, this is nice. Look at the derivative is by coordinates. You just take the derivative of the vector function, coordinate by coordinate. So here's r prime, which gives me the slope of the tangent to the curve at any point, which is what we had before. Hey, Joshua. No. It's what we had in regular old Calc 1. Increasing a dimension doesn't change the tangent from not, so it's not a tangent anymore. So we get a tangent. But what we actually get is when we put in, I picked pi out of thin air. When you put in pi for t into r prime, that's the slope of the tangent. It's the direction vector of the line. And then put in pi into the original function. And you get the location of the tail of that vector. But I'm using it as a point. Because now, if I wanted this line, the line would just be this vector times t plus this point. And let's take a look at this direction vector. If I'm looking back at the curve, let's go back to the curve. So to figure out what this line tangent looks like, I need to think, I got to get some coordinates on this thing. So for instance, when t is equal to 0, I'm going to be turns out to be at this point. So t equals to pi will be over here. And if you look at that vector, the tangent there is going to be, its y coordinate is increasing because the y's are going from left to right. The y coordinates are increasing, but the z coordinates are going down. So the z coordinates are decreasing. So this 1, -1 makes sense. It's pointing in the direction of this. And just for this one point, that vector is actually not changing in x coordinate for that one point. There's other places where, of course, the x would be changing. But in this one point, the x coordinate's not changing, so that 0 makes sense too. And then remember, this is just the tail of the vector. That's the coordinates of this point. -1 on the x, and I can see that I'm behind the zy plane. Pi on the y, I've come out this far from the z-axis. I'm over here. And 0 on the z, meaning I'm not up or down on the z-axis. So I can see this vector. I can kind of see it. It's this little guy that's tangent there at the point of tangency. So that's what's going on with vector functions as curves.